Today I'll be talking about series and parallel AC circuits. An AC circuit carries a current that changes direction periodically, usually in the shape of a sine wave. It's the type of current most commonly used in transformers, power transmission, and household electricity. AC circuits usually contain inductors, resistors, and capacitors. In these circuits, the inductor causes the current to lead the voltage by 90 degrees, while the capacitor makes it lag by 90 degrees, as shown in the graph. Impedance is a vector quantity that combines both magnitude and phase, and it can be written in either rectangular or polar form. It can also be converted between the two, as shown. In an AC circuit, the voltage follows a sine wave and is given by V max times the sine wave of the angular frequency multiplied by time. The DC equivalent value is found by dividing V max by the square root of 2. In a series AC circuit, the total voltage is the sum of the voltages across each component. In a parallel AC circuit, the voltage is the same across all components in each branch. The current in an AC circuit is given by the maximum current multiplied by the sine of the angular frequency times time plus the phase angle. The DC equivalent is found by dividing the maximum current by the square root of 2. In a series AC circuit, the total current is found by dividing the total voltage by the impedance. In a parallel AC circuit, the current through each branch is calculated by dividing the total voltage by the resistance or reactance of that branch. Finally, the special formula shown below is used to calculate the total current. Ohm's law can also be applied to AC circuits by using impedance. In an AC circuit, impedance is the combined effect of resistance and the reactance from the inductor and capacitor. The total impedance is shown on the slide. In a series AC circuit, the total impedance is the magnitude of the resistance and reactance. In a parallel AC circuit, the total impedance is found by taking the inverse of the sum of the reciprocals of each individual impedance. In this example, we're given the resistance and reactance values. We can substitute these into the series impedance equation to find the total impedance, which is 29.72 ohms. The total current is then calculated by dividing the total voltage of the circuit by the impedance, giving a current of 4.04 amps. In the parallel circuit example, we first need to find the individual impedances of the capacitor and resistor using the equation shown. Then we substitute these values into the parallel impedance equation and solve to get the impedance vector in rectangular form. Finally, we can convert this vector into its polar form to find the total impedance.